In this video, I'm going to introduce you to spectroscopy and then talk about infrared spectroscopy. So spectroscopy involves an interaction between matter and light. Light is also known as electromagnetic radiation. Now, don't get confused between spectroscopy and mass spectrometry. Mass spectrometry did not involve interactions between matter and light, but the names sound very similar. With spectroscopy, light can be thought of as waves of energy or packets of energy called photons. And properties of light waves include wavelength and frequency. Wavelength is inversely proportional to energy, whereas frequency is directly proportional to energy. You may remember a physics equation, E equals h nu, where energy is equal to h, Planck's constant, times the frequency of the light. Here is the electromagnetic spectrum, which shows the range of possible frequencies of light. The higher energy light, such as X-rays and gamma rays over here, have a higher frequency and a lower wavelength. The lower energy forms of electromagnetic radiation, such as microwave and radio, have a smaller frequency and a longer wavelength. Different regions of the spectrum can be exploited to find out information about different aspects of molecular structure. So for example, in IR spectroscopy, we exploit the infrared region, and that's going to tell us about the types of functional groups present in a compound. We can use the visible and ultralight region to detect conjugated pi systems. And with NMR, we're going to use radio waves, and that's going to tell us about the specific arrangement of carbon and hydrogen atoms. So matter exhibits both wave and particle-like properties. Matter on the macroscopic scale really appears to exhibit continuous behavior rather than quantum behavior. However, when we get really small, down to the molecular scale, we start to see quantum behavior. So for example, a molecule can only rotate or vibrate at particular quantized energies. For electrons in covalent bonds, there are very particular energy levels that are separated by gaps. And if you have a photon of light that's absorbed by a molecule with the exact amount of energy in one of those gaps, the light is absorbed and the molecule is excited. Infrared light, in particular, will cause molecular vibration. And different types of bonds absorb different IR energies, which is why we can use IR spectroscopy to figure out the types of functional groups a molecule has. Bonds in molecules vibrate in two ways. They can either stretch or they can bend. And there are different types of stretching and bending. So in a stretching vibration, the bond is elongating or shortening. In a bending vibration, bond angles, not bond lengths, are changed. And we're going to focus mainly on the stretching frequencies. So this actually shows the 6 main ways that stretching and bending can occur. So with symmetric stretching, the bonds are stretching in sync with each other. With asymmetric stretching, they are out of sync with each other. And then we have wagging, rocking, scissoring, and twisting. Those four, the wagging, rocking, scissoring, twisting, are all different types of bending. So how much energy is needed to cause a bond to vibrate? Well, it depends on the type of the bond and the energy gap between those different energy levels. So for a CH bond, there's a pretty large energy gap, but for a CO bond, there's a comparatively small energy gap. So you would need less energy to vibrate a CO bond versus a CH bond. An IR spectrophotometer is the machine that performs the IR. It irradiates a sample with all frequencies of IR light, and then the frequencies absorbed by the sample tells us about the types of bonds, hence functional groups, that are present. In practice, the samples are typically deposited on a sodium chloride plate, although they can be dissolved in a solvent or embedded in a potassium bromide pellet. This is what the IR absorption spectrum looks like. So here on the x-axis, we have the wave number. I'll discuss that in a second. And then here on the y-axis, we have the percent transmittance. So transmittance means that if you have 100% transmittance, that means that all of the IR light at that particular frequency was transmitted through the molecule and none of it was absorbed. So when we dip down to these lower values, that indicates absorption of light. Because if we only had 20% transmittance, we must have had 80% absorption. So notice how these curves dip down. They're sometimes called peaks, but they're also called absorption bands. So every time we see a dip, a band, that indicates that absorption happened in that corresponding wave number range. So the unit that's used in IR is the wave number, and the wave number is defined as 1 over the wavelength. Wavelength being measured in centimeters, and therefore the wave number is centimeters to the -1. The values range from 400 wave numbers to 4,000 wave numbers. So remember that energy is directly proportional to frequency and inversely proportional to wavelength. So here are some of our basic physics equations. So here's my question. Does a large wave number correlate to a higher energy or a lower energy? It's important to get that straight in your mind. When we're looking at an IR spectrum, there are 3 important characteristics that every peak or band has. Where it's occurring, so what is the wave number, its intensity, and its shape. In order to talk about the wave number, we want to think about Hooke's law from physics. And in IR spectroscopy, we think about a bond as being 2 balls connected by a spring. And whenever you have 2 masses connected by a spring, that can be mathematically described with Hooke's law. Hooke's law tells us that the frequency of the vibration is related to the force constant, or the strength of the spring, or in our case, the strength of the bond holding those 2 atoms together. And then it is also inversely proportional to the reduced mass. So here is the mathematical representation. So the wave number is equal to 1 over 2 pi times the speed of light, times F, which is the force constant, which is the measurement of bond strength, divided by the reduced mass, which is defined here. So it's m1 times m2 divided by m1 plus m2, and it's the square root of that. So from this, we know that since F is in the numerator, the higher the force constant, the greater the bond strength, the higher the wave number, or the higher the stretching frequency. However, if this number gets bigger, because we have heavier atoms, since that's in the denominator, this number will get smaller. Let's check to make sure that the equation matches observation. So let's look at these 4 bonds. CH-CD, D is deuterium, a heavier isotope of hydrogen, CO, and CCl. So C bonded to H. H is a very light atom, and that is a large number, 3,000 wave numbers. When we convert the H to a deuterium, so we're getting a heavier atom, that wave number decreases. When we go to an even heavier oxygen atom, again, that decreases. And then when we go to the heavier chlorine, again, it decreases, because we're essentially increasing the number in the denominator, which is going to make that wave number smaller. Now, what about the force constant? So let's look at these examples. So a triple bond is stronger than a double bond, which is stronger than a single bond. So we're going to compare bond strength by keeping the atoms the same, but changing whether we have triple, double, or single bond. So the strongest bond has the highest wave number. So that makes sense because this number would be in the numerator, and if it increases, then the wave number increases. Then if we go to a double bond, we're reducing the value of the force constant, so we're reducing the wave number. And then finally, if we go to a single bond, we reduce it even further. The wave number formula, in addition to empirical observations, allows us to look at a spectrum and designate regions as representing specific types of bonds. So bonds to hydrogen tend to be in this region because hydrogen is so light. And then triple bonds tend to be in this region because those are strong bonds, followed by double bonds, and then our single bonds are down here. When looking at a spectrum, the area between 400 and 1500 is known as the fingerprint region. This ends up being pretty complex and difficult to analyze, so in this class we're going to ignore it. And we're going to focus instead on this region between 1500 and 4000, appropriately called the diagnostic region. This is where we're going to get a lot of information about our functional groups. Look at these two IR spectra for butanol and propanol. So they have the same types of covalent bonds. They have an alcohol functional group, they have C carbon-carbon bonds, carbon-hydrogen bonds. So really, these spectra look very similar, and it would be hard to distinguish between them based on IR alone. We can distinguish between CH bonds if the carbon has a different hybridization. So for sp3 carbons attached to hydrogens, we see those CH bonds around 2900 wave numbers. If that carbon's sp2, that ends up increasing to 3100, and if it's sp, we see that around 3300. The reason for this is that the higher the S character of the carbon, the stronger that carbon-hydrogen bond, because those orbitals, the higher the S character in the orbital, the more it penetrates the nucleus, which results in a stronger bond. So here are some examples. Here we see for an alkane, the CH bonds are all below 3000. For an alkene, that CH bond where the carbon's sp2 hybridized is to the left of 3000. And here at 3300, we see the CH bond where the hydrogen's bonded to the carbon of an alkyne. Now it is possible that an alkene or an alkyne could give an IR spectra without any signals above 3000 wave numbers, and that would be if these R groups were not hydrogen, so they didn't have any carbon-hydrogen bonds. The strength of the covalent bond is also affected by resonance. So if we look at the carbonyl bond in a ketone, that has a stretching frequency of 1720 wave numbers. However, if that ends up conjugated to an alkene, it lowers the wave number to 1680. That's because I have a resonance structure, an additional resonance structure I can draw here using that alkene, which therefore weakens the carbon-oxygen bond. So a single bond is weaker than a double bond. So if resonance means that you have more single bond character, then that's going to result in a lower wave number. And this just illustrates what I said. So the more delocalized the pi electrons, the weaker the pi bond. So here we have a ketone that does have a resonance structure. So there's two different structures. One has a single bond, one has a double bond. But then when we add that other double bond here, the carbon-carbon double bond, we have a third additional resonance structure. So now two of the three structures have a carbon-oxygen single bond versus just one that has a carbon-oxygen double bond. And the same trend is seen with esters. A conjugated ester has a lower wave number than a plain ester. So the second characteristic is the intensity. The intensity refers to how far down does the signal go? How far down does it dip? Which is really indicating how much is absorbed. So if we have a very low percent transmittance here, that means almost all of the energy was absorbed, versus a weak signal which doesn't dip down as much, so less of it was absorbed. The factors that determine whether or not a signal is intense has to do with a couple things. One of those is that the dipole moment oscillates, it changes when a bond undergoes a stretching vibration. So recall that the formula for a dipole moment, which you may have learned in Gen Chem, is, so this is the symbol for dipole moment, it's the distance, it's the charge times the distance between the charges. And this oscillating dipole moment creates an electrical field surrounding the bond. The more polar the bond, the greater the dipole moment, and the greater the opportunity for interaction between the waves of the electrical field produced by that changing dipole and the IR radiation. So greater bond polarity equals more intense IR signals. So this ketone is polar, and that carbon-oxygen bond is much more polar than this carbon-carbon double bond. Therefore, this will give rise to a weak signal, where this will give rise to a strong signal. And here's a picture of that. If a bond is completely symmetrical, then there is not a dipole moment, and we don't observe any signal in the IR spectrum. In addition to the dipole moment, intensity is affected by the number of bonds of the same type that are vibrating. So if you have a lot of some type of bond, then that's going to give rise to an intense signal. So while CH bonds are not very polar, in fact, we would consider them nonpolar, although they're not perfectly nonpolar, they often give very strong signals, and that's because there are so many of them frequently found in an organic compound. And this effective concentration on intensity is exploited with things like the Intoxilyzer 5000, which can be used to determine blood alcohol levels by determining the strength of the CH bond stretching in blood samples. The final characteristic of the signal is its shape. Some are broad, as shown here, while others are very narrow. OH stretching signals are often quite broad. OH bonds give rise to broad signals because you have hydrogen bonding that's occurring, which is weakening the OH bond, and also the degree to which any particular molecule will be participating in hydrogen bonding will vary. So you'll actually have molecules with varying OH bond strengths. So you'll get what seems like a range of signals, which is what broadens the signal. Now, if you have a very, very dilute solution that inhibits hydrogen bonding, and the OH signal becomes much more narrow. It is possible to see two OH signals, one that's broadened out because it's hydrogen bonding, and one that's sharp because it's not. The OH stretch for carboxylic acid tends to show up around 3000. So you end up seeing a smooth curve on the left, and then it starts overlapping with CH stretches, so you get this characteristic pattern. With just an alcohol, that wave number is around 3400. Hydrogen bonding tends to be more pronounced in carboxylic acids than alcohols because they can form dimers, shown here. Primary and secondary amines exhibit NH stretching signals. A primary amine is a nitrogen bonded to two hydrogens and then an R group. A secondary amine has a nitrogen bonded to two R groups and has one hydrogen attached. So with primary amines, we have these two NH bonds. They exhibit two signals, whereas secondary amines only exhibit one signal. So here we have a primary amine, and notice these two dips. Those are the two signals, versus a secondary amine, we only see one dip. So why are we seeing that distinction? The reason is that the two NH bonds can vibrate either together in sync or not together out of sync. When they're in sync, it's the type of stretching called symmetric stretching, but when they're out of sync, it's asymmetric stretching. So at any point in time, half the molecules are stretching symmetrically, whereas the other half are out of sync. So when analyzing an IR, you want to focus on the diagnostic region, and you want to look within that region for double bonds, triple bonds, and hydrogen bonds to oxygen, carbon, nitrogen. Then you want to analyze the wave number, intensity, and shape for each signal. When looking at the 2700 to 4000 region, try drawing a line at 3000. Things that come to the left of the 3000 line are very distinctive, and you can figure out a lot of information from that. So sometimes if you're doing a reaction, you would use IR spectroscopy to figure out if you were successful in making your product. So suppose that you did this reaction shown here. You oxidized an alcohol to a ketone. How could you figure out if you successfully made the product by analyzing it with IR? What would you look for? Well, you would look for the presence of a carbonyl stretching frequency, which has a distinctive range, and you would look for an absence of the OH signal. Finally, test your knowledge. So what type of information can you get from an IR spectra? The molecular weight, the types of functional groups it contains, the molecular formula, or the number of hydrogen atoms. Also, which of these bonds will have the largest wave number and why? A CH bond, a carbon-deuterium bond, a carbon-nitrogen, or a carbon-bromine bond. And that is it for this video.